All right, how should I rearrange this now? Tell me how I should rewrite this if I want to look at how it reacts. Boy, it'll be xenon 4F14, 5D10, 6S2, 6P2. Can you reach it?
Yeah, I got it.
All right. Now tell me what the valence electrons are. How many valence electrons does lead have? 4. It has 4. It's the highest n. What's the highest n? 6. When n equals 6, how many total electrons do we have? 2, 4. There are 4 valence electrons for lead. These ones are going to be inner shell. These are outer shell or valence electrons. Valence electrons are called outer shell electrons. All right, tell me what are the common charges? What do you guess are the common charges for lead? 2 and 4. Exactly. Lead 2 and lead 4. Common charges. We can look that up on Wikipedia. Lead. Well, actually, it's you could lose 1. Plus 1 would be one of the p electrons. Plus 2 would be both p electrons. Plus 3 would be one of the s electrons. Plus 4 would be both s electrons. The most common charges are plus 2 and plus 4. Plus 2, an oxidizer comes, plucks these 2 off. That's plus 2, leaves us with 6. This 2, and another or the same oxidizer can come and take 2 more. What about plus 5? No, you wouldn't expect plus 5. I mean, the 5D is filled. You know, it's like having a perfect cake. You don't want to touch that perfect cake and ruin it by eating a slice of it and then leave it in its pristine state. Throw it in the freezer so you can admire it later. No, eat it. Yeah, it depends, you know. It's not to say it can't happen. It can happen, you know. Just there has to be certain circumstances. So it happens for copper. You know, copper is funny because copper is this. Copper is argon, 4s, 4s1, 3d10. And so if we rearrange copper, it's going to be argon, 3d10, 4s1. So if this is copper, what would you expect its charge? Well, how many valence electrons does copper have? 1. So plus 1 should be it. And you wouldn't expect it to lose that d electron because that would screw up the 3d. The 3d is perfect. You know, you don't want to screw it up. But when we look at copper, it turns out that, you know, plus 2 is the most common charge for copper. And so copper 2 plus actually screws up this D. And when we get copper 2 plus, which is the most common charge for copper, we get argon 3D9. And we think, we just screwed it up. But it isn't screwed up because 3D9 for copper is stabilized in a different way. What happens with copper is this. They don't have a good one. When you get copper in a 3-dimensional structure, you know, it looks like it's this D9, which is screwing up that nice symmetry. But what happens is it looks like what happens is in that structure, it screws up all the d orbitals. The d orbitals no longer become degenerate. So these are the 5 d orbitals. 1, 2, 3, 4, 5. Well, what we see is splitting in the d orbitals. This is in Chem 1b. The splitting results in a structure or a pattern like this. And a pattern like this, D9 is preferred, D9 or D8, because we can get more electrons in lower energy orbitals versus higher energy orbitals here. And so there's a reason for D9 occurring in copper, but it wouldn't occur in something like zinc, you know, because it has a different kind of structure and its compound complexes. So this is the kind of stuff we see. But for the most part, you know, you guess that the Ds aren't going to be attacked. You're right. You know, the D10 is stable. F14 is stable. They're filled. And so we aren't going to touch these, especially in lead. Do you see lead plus 5? Oh, I don't see lead plus 5 there. I'm not going to touch it. However, these are susceptible to attack. And so anything that's partially filled, like a partially filled D's, no problem attacking that. And so if we look at something else like iron, iron has 2 valence electrons, you know, the 4f2, but the 3d, it's 4f2, 3d6, and so those can be attacked as well. So when we look at the oxidation states, we see a pretty wide range of oxidation states. Okay, other questions?
You know how copper takes the electron from the S to the D
Yeah.
orbital? Does that happen for silver and gold?
Yes, it does. It becomes less pronounced. You know, you see more exceptions as you go down. The reason is that you see more exceptions as you go down is because the energy spacings shrink. I mean, the orbitals get closer and closer and tighter together. And so let's see if we can get a decent energy level diagram. Probably not. It doesn't show the splitting in these, but what happens is we go from n equals 1, which is lowest energy, all the way to n equals infinity. Now, how far away is n equals infinity? It's here. N equals infinity is right here. That's n equals infinity. And so you have to draw an infinite number of lines between here and here. Because beyond, you see the blue region? That's beyond infinity. That's infinity in terms of the electrons, energy here. And so the spacings become incredibly tight up here. You got to draw so many lines. Well, that happens in the quantum mechanical energy level diagram as well. For this stuff. This is for the hydrogen atom. But we don't have, there are no diagrams that show it, unfortunately. Oh, here's one. That goes up to n equals 8. But do you see how things start to get more tighter and tighter? The biggest jump is 1 to 2, and then 2 to 3, and 3 to 4, etc. And so the the energies converge, you know, but the radius or the size of these diverge. All right, and so the question was about this. And so copper, yes, does that exception. Silver, yes. Gold, yes. But there are more exceptions that come out here. And so there's this weird one already. When you get to here, the D and the F are so close in energy, you know, and so we fill one of the D's and then move on to the F and then refill the remaining D's. It's because the energy spacing is so small. There are going to be more exceptions as you go down. And so you might not always hit it correct, you know, on how you do it. Chromium is an exception. Molybdenum, yes. Tungsten, yes. And so let's take a look at the electron configuration for tungsten. Well, actually, let's go to gold. That might be easier to do. Misspelled it. And so do you see a S electron here was sacrificed to complete the D? You know, gold should be 6s2, 5d9, but it came out 6s1, 5d10. All right, are there other questions? Uh-huh.
How do you determine the polarity of a molecule if that molecule has more than 2 atoms?
If it has more than 2 atoms, how do you determine the polarity? Do you have a particular molecule in mind? Okay. Here we have a big molecule here. Is this polar or nonpolar? Well, how about this? COH. Is this area polar or nonpolar? This is kind of water-like. Rather than HOH, it's COH. C and H have a very similar electronegativity. So this end is polar. However, this end is nonpolar. But overall, this polarity is not canceled out. And so we call this polar. This is a polar molecule. And so we look at, when we get to bigger molecules, like for example glycine we did, is glycine polar or nonpolar? And so we can just quickly look and see. When we look at glycine, this would be, is this glycine? No, this is the protonated form of glycine here. There would be one hydrogen missing here. And so this is the glycine cation. It has an extra hydrogen here. It's a proton. But this one's going to be polar. I mean, this is like ammonia, it's polar. This is like, oh no, this is like ammonia, it's polar. This is carboxylic acid. Actually, this is wrong. This is not glycine. I think somebody was just trying to make a cute molecule. There's a problem with this one though, because if this nitrogen is protonated, this hydrogen, this oxygen should be protonated also. This would be glycine here, I think. So we see this is polar, the carboxylic. This amine part's polar. This is non-polar. So this whole thing's polar. And so for bigger molecules, we just look at it in terms of regions, polar regions, non-polar regions, that kind of thing. And so if you had a specific molecule, then we could take a look at it. where something like CO2, CO2 is tricky here because the polarity cancels. You know, you got one polarity pointing one way, another dipole pointing the other way. They cancel each other out. They're equal and opposite. So CO2 is nonpolar. This would be polar because they wouldn't cancel out. That would be polar if it adopted this structure, but it doesn't adopt this structure. It adopts a linear structure like that. I don't know what these are trying to show because it's non-polar. If the angle were like this would be polar. There. All right. Yeah, I don't know what this thing is showing. We could see in quantum mechanics what we do is we call we map this out, and these are called electrostatic potential, electrostatic map. So this is water here. Red indicates negative, blue indicates positive. So that's water. This would be like CO2 here. I think this is CO2 here. So the oxygens are red, carbon's blue here in the center, and these are equal and opposite. So this pole cancels out this pole here. And we can see depending on the molecule itself. This is acetylene here. Acetylene is a carbon-carbon triple bond here. This is nonpolar as well. You see. It's nonpolar for two reasons. One is that gymnastics. I don't know how that got in there. There, this is polar. You can see how things don't balance out. If they don't balance out, it's going to be polar. And so this is what that is.
Do polar bonds only form in nonmetals?
No, you mean non-metal only? No, polar bonds can form between metals and non-metals as well. Those are the most polar bonds. The most polar bonds are called ionic bonds. Those are the most polar. And so let's take a look at the electrostatic map of an ionic compound. Let's go ionic versus polar covalent versus non-polar covalent, just covalent. Do that, see what we come up with. Electrostatic map. This would be it, except they got the color coding wrong. Shoot. The color coding's all messed up. Normally, you know, I always think of red as being positive and blue as being negative. In this case, or black is negative. But when we do this using computers, the red comes out negative, and that's just the chosen convention. But you can see the nonpolar band on the left, and then we start to get more polar, which is hydrogen chloride. Chlorine's non-metal, and hydrogen's a non-metal. And then we get the most polar. You see how red the sodium is in this case, and the chlorine is. But this is not a computer simulation. Let's look at a computer drawing from quantum mechanics. To do that, this would be it. This is electrostatic potential map. And you can see on the left is hydrogen, in the middle is HF, which is polar covalent, and on the right is sodium fluoride, which is ionic. And you can see the sodium is practically all blue, and the fluorine is practically all red, showing that's the most polar. The most polar are going to be between metals and non-metals. They're going to have the greatest electronegativity difference. These electrostatic maps are kind of helpful for gauging it. This is more showing the polarity, sharing and non-sharing of electron cloud. There. Some more maps here. Is this molecule polar or non-polar? Yeah, it looks polar, but it's actually non-polar because everything cancels out. In this triangle here, this would be non-polar. It's non-polar based on the bonds, but if you look at it, it's BF3 minus, and so it's an ion. Ions are very polar because they have a negative charge. But in terms of the distribution, it's evenly distributed. And so there's two different polarities. Two ways we define polarity. One way we define polarity is it doesn't look, all that symmetric. And so this is very non-polar because it's very symmetric. Right? And the other way we define polarity is based on the charge. And so for a sodium ion, some people call a sodium ion nonpolar. Why do they call a sodium ion nonpolar? They call it nonpolar because it's just a ball, a sphere. It's not distorted at all. On the other hand, sodium ions are very polar because it's a monopole. A monopole just having one charge. And so in that sense, it's very polar. And so ions are very polar because they have a charge, but how that charge is distributed could be symmetric, which we tend to associate with nonpolar, or asymmetric, which we tend to associate with polar. So some people call ammonium, what would you call ammonium? Polar or nonpolar? Let's take a look at the structure for ammonium, NH4+, plus, and we're going to look at the electrostatic map for ammonium this time. I'm going to draw up the electrostatic map. Electrostatic map. NH4+. Plus. Okay, maybe I'd better narrow the electrostatic potential map. Well, it's not coming out. But it would look very symmetric. So some people might say, well, it's nonpolar because it is very symmetric. It's tetrahedral in its shape. And the other people will say it's polar. It's polar because it's a monopole. It's got a positive charge. Both are right in their own respect. That's because there's two ways we look at polar and nonpolar. All right, other questions?
When we draw the Lewis diagrams of the molecules, and you know how there's different structures of how to draw when we draw the Lewis diagrams of the molecule.
Mm-hmm.
When can we determine if it's the wrong structure by the formal charge?
We use two ways to determine if it's the correct set, or actually, right or wrong. We use two ways to determine the energetics. We usually go for the structure that has the lowest energy. So sometimes we can't avoid formal charges. Sometimes we can't avoid violating the octet rule. You know, but we're always looking at minimizing. Now, if we have a choice between two structures, one structure has formal charge, the other structure has no formal charges, we pick the one with no formal charges. That one should be more stable, right? There's no winner, there's no loser, everybody breaks even. Or we have a structure that has octets versus a structure that doesn't have an octet, we're going to take the structure that has an octet. That's when we have a choice. Sometimes we have no choice, though, and there's nothing we can do about it. And so a case where we have no choice is something like boron trifluoride. Boron trifluoride here is we're going to have to sacrifice one or the other to make this work. One, if we draw a boron trifluoride like this, then this is great because there are no formal charges. But it's bad because boron doesn't have an octet. And so one thing we could do, because we're limited, we only have 8 times 3, we only have 24 electrons possible, we're going to have to form a double bond. If we form a double bond like this, then everybody has an octet. If everybody has an octet, it should be good, right? But then you also have to consider formal charge. Now, the formal charge here is fluorine's going to have what formal charge in this case? What is it? +1. And boron has a formal charge of -1. So essentially, we can't have both. We can't have formal charge being minimized and an octet at the same time. So we got to pick one or the other. And so which one of these two are you going to pick? Are you going to, go, well, octet is more important, or are you going to go formal charge is more important in this particular instance, because we cannot do both at the same time for this. And so for this particular molecule, we got to pick one of those. Which one would you pick? Normally what we do is we would pick the octet. The octet normally takes precedence, except for fluorine. If we look at the electronegativity, this is electronegativity from Wikipedia. Fluorine tops the electronegativity chart at, what's fluorine's electronegativity? 3.98, or let's just call it 4.0. Fluorine is a 4.0. What's boron? 2. So boron, and if this formal charge, if these formal charges were accurate, this basically tells me that boron took an electron from fluorine. Is that likely to happen? No. And so we come up with a rule. The rule is this: fluorine never forms a double bond. In order for fluorine to form a double bond, its formal charge has to go to +1. And that means it has to lose an electron to whatever it's bonded to. But whatever it's bonded to is going to be weaker than fluorine, because fluorine's at the top. So it just doesn't make sense for fluorine to form a double bond. So fluorine never forms a double bond. And so that's why we're left with this structure. But we use both. We use both formal charge and octet, and we memorize some simple rules here and there. And the simple rule would be fluorine never forms a double bond. There are other simple rules too. Sometimes you can't sacrifice. The classic example of something that still doesn't quite make sense in terms of sacrifice is carbon monoxide. If we draw carbon monoxide like this, so here we've completed the octet. on oxygen. Now, is it possible to complete the octet on carbon? Well, what are the formal charges in this particular molecule here? Carbon is 0. Oxygen is 0. So you might go, oh, this is good. Based on formal charges, everybody breaks even. However, the octet rule has not been, because carbon has less than an octet. Well, we can give carbon an octet, but at what sacrifice? Well, yeah, we got to form a triple bond. Who's going to sacrifice the electrons for the triple bond? Well, it can't be carbon, because if carbon sacrifices electrons for the triple bond, it's still going to be left with less than an octet. And so the only thing that can happen here is oxygen has to sacrifice the electrons for the triple bond. Now, does everybody have an octet? Yes, everybody has an octet, but what are the formal charges? Yeah, -1 on carbon. Wait a minute, does that make sense? And a +1, or is it got to be switched around? It should be switched around, because which one is more electronegative, carbon or oxygen? Oxygen is more electronegative. But it can't be switched around. This is it. So if you want an octet on both atoms, it's got to be this way. It's got to be that carbon gets the electron, oxygen loses. Right? It's got to be this way. It's got to be this way, but maybe we'll be like BF3. Does BF3 have an octet? No, we're just going to sacrifice the octet, because do you think oxygen is going to be very happy giving up to carbon? Carbon, who's strong? Well, let's take a look. Carbon versus oxygen. Oxygen's stronger. Oxygen's a 3.5, let's say. Carbon's a 2.5, roughly. And so will this happen? Should I make rule number 2? Rule number 2, oxygen does not triple bond. Should that be rule number 2? No, it's not. Fortunately, I don't have to list off a whole bunch of rules, because that would be too much to memorize. But the fluorine doesn't form a double bond is a good rule. This is not a rule. In fact, you know what? This is the way it is. This molecule, carbon monoxide, has some interesting chemical properties because of this. Carbon monoxide and cyanide are like this. Cyanide's like this. Cyanide has a negative charge. This whole thing is negative, though. Nitrogen's 0. This whole thing's 0. Carbon monoxide and cyanide are very powerful, what we call Lewis bases, because of the negative charge on the carbon. It makes it. And carbon monoxide and cyanide are very poisonous to hemoglobin, the hemes in particular. And so let's take a look at the electrostatic potential map. These come from quantum mechanics, quantum mechanical calculations. Electrostatic potential map of carbon monoxide, CO. You look at the electrostatic potential map of carbon monoxide, you see red. Is red positive or negative? Red is, it's always confusing, because red terminals on batteries are the positive terminals. And Spartan is a very popular quantum mechanics calculation program. But if you look at red, is red negative or is red positive? red is negative. This is electrostatic potential map. It's in certain units of energy. Red is negative. It doesn't help that people screw it up and flip it the other way, but from quantum mechanical calculations, red is negative. So this is the carbon over here. See the oxygen. Sizes are screwed up on this one, so it's confusing. All right, let's take a break here and then we'll continue. There are going to be certain cases where, where it's a little bit trickier, but for the most part, we look at completing the octet, the main priority. Completing the octet unless you have fluorine, and then it won't complete. Fluorine sacrificing. Oxygen here did sacrifice, and we completed the octet. Okay.